Okay, so the point of this video is to make a quick demo of my image-based visual positioning system that I've been playing with for the last few days, and get some feedback and see if someone wants to give me some data to play with. So basically what I've done is that I've bought an image from Skyfi. Skyfi is a great app that allows you to buy satellite imagery very easily. So I bought this image, which is an area of Austin in Texas, which is quite a large image, 7,000 by 7,000 pixels, something like that. It's about 100 megabytes. And the area, I don't know, you can sort of guess from the size of this. It's a few kilometers by a few kilometers. I think it has to be 5 by 5 or something like this. It's the smallest size that they allow you to buy, actually, because I was just playing around with it. So I bought this image, and the cool thing is it's very high resolution. This is 0.3 meters per pixel, if I remember correctly. And of course, since it's a satellite image, it's georeferenced. So for every pixel of this image, theoretically, we can get a GPS position. And not just theoretically, it actually works, as you'll see in a second. So what I've built is a sort of very low-res flight simulator based on this. Let me start it here. And so what this does is it makes a mini-map out of this image I just showed you, or any image that I give it, really. And it creates a kind of virtual drone or virtual helicopter or whatever you want that starts at the center here and flies around the map. And so what happens is every few seconds, it's set to 10 seconds right now, this thing, right now it's a little arrow the way it's showing here, this thing moves by some random amount in a random direction, and it creates a new image here as an output, which is sort of what you would get from a downward facing camera that's positioned on the drone or helicopter or whatever you want. Let's just call it a drone for the rest of this discussion, because I'm going to keep saying that over and over otherwise. So you can see it's moving along, it's updating this little path, and it's creating a new image like this every time it moves. So this image, as you can see, I have an estimated latitude and longitude here, which is the center of this image, which I'm getting from the georeferencing data from the big image. And so this is just cropping a small piece of the big image as it goes along. Right now it's cropping always at the same size, but I've run a bunch of tests previously where I'm kind of simulating different altitudes and perspective distortion and that, but that's more complicated, and I'm not going to go into all of this into this video. And so what this does, it just outputs a file called current location here to the file system. So what we're going to be doing is using this file in a separate system which doesn't communicate with this process at all, so it doesn't have access to the GPS location, to try to find where this drone is flying in space. So the obvious use case is if you're flying with no GPS, or in a situation where GPS gets jammed or something like this, if you have these preloaded satellite images and you have this system running, you can estimate the position of your drone relatively well using just these visual cues. So I'm going to start this algorithm here. And so you see it's in a folder called LightGlue, because I'm actually using LightGlue, which is a cool neural network based matching algorithm for the image matching, but there's a bunch of other things going on in there too. So let me start this. And so what's going to happen here is this is actually initialized just in the code from the center point here. So it's starting by searching around the center point for a match to the current location image. So this is loading tiles from this map, which are in a separate folder, which are also georeferenced, very simply just cutting this into georeferenced pieces. See, it says saving file, which means it's found the current location. So it's moved outwards from here and found the location. Once it's found it, it only searches every 5 seconds because we don't want to be running this forever. So if I look in matches here, we have some waypoints. So this is the first waypoint. Estimated, you can see it's moved on a bit here, but it's similar to this location. And so we're estimating latitude and longitude here from just these images. As you can see, it's pretty close. This match is not perfect because, as you can see, the center point of the match is very far kind of off center, which I write here, centroid offset 27% towards the southeast in the matching image. So it's not perfect, but let's move on and look at some more. So Waypoint 2, this one's probably a bit better. And as you can see, it's pretty much keeping up with the flight of this drone. Occasionally, so what it's doing is actually based on momentum of the previous movement. It's estimating what the next tile should be for the search. And so it's doing a pretty good job of keeping up here. As you can see, it's keeping up when it only does one search per image. And as you can see, when it only does one search per image, it's insanely fast. It's like on this desktop machine, it's like 1/10 of a second. But it also actually doesn't use much resources. If we take a look here, this thing has a tendency to pop on top. Let's have a look at GPU usage. Here, as you can see, it sort of hovers around 3 to maximum 5 gigabytes of GPU usage, which means you could probably run this quite efficiently on a Jetson Orin or something that you can actually build into a relatively lightweight drone. My next thing I want to try actually is putting this on a Jetson Nano. I don't have an Orin. I need NVIDIA to send me one or borrow one from someone. If you have an Orin, send it to me and I'll play with this on the Orin. But so anyway, as you can see, we're only doing one search every few seconds when it's easy to find the location. And then if the flight simulator here suddenly jumps and tries a different location, or I could reinitialize it just for the test. There we go. So we lost the location. So now we're actually running a wider search and doing some optimization and things like this. And hopefully it'll lock back on in a second. So in the meantime, we can look at these waypoints. There we go, it logged back on now. And we can see, none of this is very optimized, by the way, like the tiles could be different resolutions, we could search much better, things like this. But if we go through the waypoints, we can see here 10, 11, it's actually the same location, 12, 13 didn't move, 15, 16. The searches are happening faster than the movement in the flight simulator. But let's move on. There we go, so from 20 to 21 there's some movement. And as you can see, it caught up and found the next tile, 24, 25, 26, 27. These are all quite close to the edge, so the estimations are not perfect, but they're also like quite low down. So, I mean, low down if you're considering this to be like a vertical kind of the position of the camera. So it's still within probably like a few hundred feet of the actual location. And so moving through these waypoints, we've got up to about 30 of them now. Let's go through them, 0, 1, 2, 3, etc. As you can see, when there's not much movement, it's very easy and they lock on really well. Now it just locked on again. And there you go. So the cool thing with this is that it's a kind of purely software-based GPS-denied navigation system, or a purely software-based visual positioning system. And with very little optimization here, it's able to follow this this virtual drone very well. Obviously, I mean the simplification that we have here is that these images that I'm comparing are derived from the same map as the base map. So there's not much distortion, there's not much modification to these images. So it's a relatively simple matching case, right? I mean, as long as the drone doesn't suddenly go really far out, it's going to be relatively easy to predict the next waypoint. A few more waypoints here. But so I've actually run some other tests where I've done all kinds of augmentations and modifications to the sub image, to the image that we're trying to map to the map here. And I've tested all kinds of different augmentations, like adding simulated snow and fog and rain and stuff like this. Also perspective distortions and channel changes to be able to simulate what you actually get when you're flying a real drone, especially things like JPEG compression, like messy images, things like this. And the result is actually that the matching algorithm and the key point detection algorithm are fairly stable. So it actually gets it perfectly right. I have the numbers here, but something like around 80% of the time. Let's see. So success is 0.79. So 79% of the time it gets it right, even with quite heavy modifications. Like a lot of what I was doing with this here is really, really messy images. And another thing to bear in mind is that neither the key point detector nor the nor the matching algorithm that I'm using here are actually trained on satellite or overhead imagery. So there's a lot of headroom for making this more accurate and more efficient, and just generally quite a lot better. But as you can see from this, it's already doing a really, really good job and keeping up with the virtual drone here, which is covering quite a lot of area. Like if this was actually a quadcopter, like you can see there's a football field here, the size of that football field, it's already traveled, I don't know, like maybe 6 or 7 times the length of that football field along the path. And we're keeping up very well here. Oh, something crashed here, I guess at some point. Yeah, there was an image missing or something. I'm just using the file system here to transfer images, which is really messy. It looks like there was an image missing and it wasn't able to load it. So I can just restart this, and if I restart it, as I said, it's initialized to the center point here, which is sort of like if you were flying a drone, you would kind of input from the flight controller the starting GPS point before you lose GPS if you're using this as a redundancy feature, or just manually input something if you really need to. So I'm assuming that at some point you have GPS, and if you wanted to use this as a backup or as some kind of redundancy system, you would also be able to input these coordinates, or like refined versions of these coordinates where you're actually correcting the offset and things like this. Input them in a Kalman filter, include some other like interpolation with GPS and speed and IMU and barometry and all of these things, and get to a really, really accurate positioning system, presumably. And so that's kind of the next step here. Now I have some of my existing drone customers that are set to provide me some data that's kind of more real world. We're going to also integrate some satellite imagery again. So buy some satellite imagery to coordinate with that and see what we can get in terms of positioning from purely visual methods like this in a purely software system, at least something that you can add without having to add extra sensors to a relatively simple drone. So as you see, I restarted this. Now it's searching all over the place again. So because it wasn't initialized correctly, it's looking a lot further. So it's going to take quite a bit more time now to lock on to where the drone is now and carry on from there. But I think that's it for this video. I think I've shown everything that I can show. And if you're interested in trying this, if you have a drone, or if you're building a drone, or you're playing a helicopter, an Airbus, whatever, I want to try this out and have some data to share with me, then send me a message. If you're watching this, you most likely know how to contact me, so there you go. Alright, that's it for today. Bye bye.